Okay, so we've talked about mass spec, we've talked about IR, spectroscopy. Um, Now it's time to get to the main entree, where we get the most information, and that's NMR spectroscopy, or nuclear magnetic resonance spectroscopy. This is the same technology that's in an MRI machine, magnetic resonance imaging machine. When they first developed those machines, they originally were calling them nuclear magnetic resonance machines, and people said, wait, if you put the word nuclear in front, no one's going to get inside this machine because they're going to be afraid of it. Um, so they just call them MRIs, but it's the same concept as what we're going to talk about now. Um, so the idea here is that some nuclei have what we call nuclear spin. You may or may not remember from a prior chem class that electrons also have spin. Um, Electrons can have what we call spin up or down. Um, that's why you may have seen diagrams where you use arrows to represent electrons as being either spin up or spin down. That represents a quantum quality of those electrons. It's one of the quantum numbers of the electrons. It can either be plus one half or minus one half. Um, all of that is very complicated, but the idea is it's this magnetic quality um, that makes the electron behave as if it's a charge that's spinning around, becoming an electromagnet. Um, so some nuclei also have this. Not all nuclei, not even most nuclei, but some nuclei have a spin. And the thing about a spin is if you apply a magnetic field, so if you put them in a strong magnetic field, um, magnetic fields are indicated by the letter B. So B applied is the magnetic field strength. It turns out that here E is representing energy. So the y-axis here is energy. Turns out that, if you start with your nuclei, the ones with positive spin and the ones with negative spin have exactly the same energy when there's no external magnetic field. But if you apply an external magnetic field, those two will diverge. So the ones that are aligned against the field, their energy will go up. The ones that are aligned with the field, their energy will go down. Um, so you end up with a split between nuclei aligned with the field and nuclei aligned against the field. All right. And there becomes an energy gap between these two. Okay. So normally these nuclei, they all have the same energy. Now they don't have the same energy. A physics term for this is they become non-degenerate, meaning they don't have the same energy. So the way NMR works is you put your sample inside a very strong magnetic field that creates this gap in energy between nuclei aligned with it and nuclei aligned against it. Um, and then, so that this delta got turned to a D. So I'm just going to replace that with a delta. Uh, you have these two possible states and you have an energy difference between them. This is how spectroscopy works, is now you use electromagnetic radiation. This here would be the energy of a photon. So if you have those two different possible states, if I hit my nucleus with a photon that has exactly the same energy as the energy gap, what it can do is get absorbed by that nucleus that's, say, aligned against the field, and it can pop it up so that it's now aligned with the field, right? So you can have you can have a nucleus absorb a photon and jump from the lower energy to the higher energy. So just like IR, we were seeing which bonds would absorb infrared light um, and use that energy to go to a higher vibrational energy. Um, Here we are using photons to promote nuclei from a lower energy state to a higher energy state. And when that delta E equals the energy of the photon, we call that resonance. That's where the nuclear magnetic resonance comes from. Um, so there are two nuclei that we will focus on. There are others, but we will focus on carbon-13 and hydrogen-1, among others. Um, and it turns out these energy differences are small, even with a very strong magnetic field. Um, these are small. Delta E is small. So what are the smallest energy photons that we have? What's that very low energy end of the spectrum? Um, so that would be radio waves. Uh, so this is the good news about an MRI. You are using a very powerful magnet, but the electromagnetic radiation you're using is not particularly powerful. And that's good because it's not exposing you to, say, lots of X-ray radiation, like an X-ray or a CT scan would. Um, this is all radiation that is low energy and is not capable of causing damage to your cells. So that's what makes it useful. All right, so this is the general idea. We use a strong magnet to get this difference in energy, and then we see what wavelengths of light get absorbed, or what radio waves get absorbed, and that will give us an idea of how big that energy gap is. So why is that helpful? Well, the frequency of the absorbed photon is going to be dependent on how strong the magnetic field is for a given nucleus. Um, so this equation here, again, we can ignore this because it's a constant. Nu here is the frequency of the absorbed photon. And that's just going to be a function of what we call the observed magnetic field strength. At a given nucleus. Okay. So what's going to affect that observed magnetic field strength? Well, to understand this part, you need to understand something about the way magnetic fields interact with charged particles. So every nucleus is surrounded by electrons. All right. I have my very highly detailed drawing of a nucleus surrounded by electrons over here. If you're wondering what this represents, this is a nucleus surrounded by electrons. And when we apply a magnetic field, So I have my applied magnetic field. What happens is electrons will start to circulate in a way that opposes the magnetic field. So this drawing here is representing the electrons circulating. And you know, electrons moving in a spiral through a circuit, through uh, a wire, is the way to create an electromagnet. Um, when electrons circulate in this way, they will tend to counteract the applied magnetic field. So the nearby electrons will induce a magnetic field that opposes B applied. All right. So if I'm thinking about what B observed really represents, it is going to be a factor of, well, first of all, the applied field, but then there's also the induced field caused by the electrons nearby. So the observed magnetic field is going to be the applied magnetic field plus this induced magnetic field, which is usually negative because it's opposing. B applied. And I will say there is one other factor to come later. But we can understand this observed magnetic field as being a function of the applied magnetic field and then this induced magnetic field. So what's going to make that induced magnetic field vary? Well, it depends on how much electron density there is around that nucleus. More electron density near a nucleus is going to cause a greater induced magnetic field. We say that electrons nearby shield the nucleus from the applied magnetic field. So the observed if we go back to the frequency of absorbed photons, that's going to depend on the electronic environment near a nucleus. So those frequencies are going to give us information about the electron density nearby an atom. That is huge because that tells us a lot about the structure of the molecule. Okay, so there are when we take the NMR spectrum of a molecule, we will get a spectrum that looks like this with different peaks. And these peaks correspond to the different induced magnetic fields around different atoms. So a picture like this starts to tell us something about the electron density near atoms. We can get a lot more specific than that. So I'm going to start by looking at carbon-13 spectra. We don't use carbon-13 NMR nearly as much as proton NMR, but it does give a very simple a very simple picture. So the things I say about carbon-13 NMR will apply broadly, and then we'll talk about proton NMR where there's going to be some other specific information we can get. But those precise absorbed frequencies are sensitive to changes in the magnetic field. So depending on how strong our applied magnetic field is, we're going to get different values of frequencies that get absorbed. To get around that, we set a standard. We set a 0 point. Just like in the Celsius scale, we set the 0 point as the freezing point of water. In this scale, we're going to set a 0 point as the absorbance of a molecule called TMS. All right, so what is TMS? TMS is tetramethylsilane. TMS is tetramethylsilane. Now, here's the thing to know. Silicon has a low electronegativity. It's something like 1.8 maybe. You can look it up on your periodic table. What that means is these bonds all get polarized toward the carbon. So the carbons in TMS have a lot of electron density around them. What that means is they are shielded from the applied magnetic field. And you haven't seen a lot of organic molecules with silicon in them. So they're going to be more shielded than the atoms in almost every other organic molecule that you've seen. So that's what makes it a good 0 point. So TMS is our 0 point. That's as shielded as we're going to see. There are some rare occasions where you see things that are even more shielded than TMS. You're not likely to encounter one in this class. And essentially what this equation up here says is we're going to define our value of chemical shift. This is what goes on the x-axis. So this x-axis is chemical shift in parts per million. We define chemical shift as the frequency absorbed by the sample minus the frequency absorbed by TMS divided by the frequency of the magnetic in the instrument. So this is the magnet strength. And this is the difference between our sample and TMS. And TMS is, remember, our 0 point. So this is saying, how different is this from TMS? And then we're dividing it by the magnet strength in our particular NMR machine to give us a consistent scale from machine to machine. Okay, that's the only point of this, is this gives a consistent scale from machine to machine. If you didn't understand any of that, that's okay, because in the end, I want you to be able to look at the NMR spectra and interpret them, and you don't necessarily need to understand all the ins and outs of where the spectrum is coming from in order to be able to read them. But if you like background, hopefully that helps give you an idea of where these pictures are coming from. So there are two major factors that influence chemical shift. The first is hybridization. So every NMR is going to be split down the middle, roughly. And we're going to have sp2 hybridization on one side and sp3 hybridization on the other. sp hybridization is more complicated. You don't encounter it as much, so I'm not even going to bother addressing it. But sp hybridization doesn't necessarily follow this split. It's not like it's further down to the left. But generally, you can separate things into sp2 and sp3 around a certain split. And then within each of those sections, anything that takes electron density away from that area is going to de-shield and push them to the left. So more de-shielded, meaning less electron density. We'll push things to the left in both cases. Anything that pushes electron density toward a nucleus is going to make it more shielded. So hybridization kind of splits our picture down the middle, and then we think about the electron density nearby. Those are the two factors that are going to affect how things show up on a spectrum. So let's look at an example. So here is a spectrum for a carbon-13 NMR spectrum for 2,4-dimethylpentane. You'll notice I have 3 peaks. And in this case, our dividing line between, for carbon NMR, our dividing line between sp2 and sp3 is going to be around 100. So like this is all sp3. But I have 3 peaks here. So the question is, well, 2,4-dimethylpentane has 7 carbons. Why am I only seeing 3 peaks? Okay, well, 2,4-dimethylpentane, 1, 2, 3, 4, 5. 2,4-dimethyl. Why do I only see 3 peaks? Well, some carbons are equivalent to each other. So for instance, these 2 orange carbons are equivalent. And these 4 purple carbons are equivalent. And then I have 1 carbon in the middle. Okay, so what I have are a set of 4 equivalent carbons, a set of 2 equivalent carbons, and then just 1 lone carbon. Each of those makes a peak. So each set of equivalent carbons make a peak. So those 4 equivalent carbons only show up as 1 peak. The 2 equivalent carbons show up as 1 peak. So that's the first thing to note, is that when you have chemically equivalent atoms, they don't show up separately in an NMR spectrum. But if you look at this spectrum, you can see, okay, I've got 3 different kinds of carbon atoms, 3 different kinds of carbon atoms that have different chemical environments. That's essentially the only information that I would get out of a carbon-13 NMR spectrum. So I'm going to go on and talk about proton NMR, which is really the main event, where I want you to be able to read these. Proton NMR is more useful, partly because carbon-13 NMR, we mentioned back in the mass spec lecture that only about 1% of carbon atoms are carbon-13. So when I run a carbon-13 NMR, it's relying on only 1% of the molecules to show me information about the carbons, which means I need a higher concentration in order to do it. Whereas 99.9% of hydrogen atoms are hydrogen 1. And so there's just a lot more of them in any sample. So in a proton NMR spectrum, our dividing line between sp2 and sp3 is going to be somewhere a little to the right of 5 parts per million, just below 5. So that's our dividing line between sp2 sp2 and sp3. Okay. So when you look at a proton spectrum, think of that, and just remember, going this way means more deshielded. Going this way means more shielded. Oh, and just for terminology's sake, we call this end downfield and this end upfield. So if you hear those terms, that's what they mean. So let's take a look at some specific functional groups. My baseline for hydrogens is a hydrogen bonded to a carbon that's not really bonded to anything else. So like an alkane hydrogen. The baseline for that is usually around 1. Okay, so you're not likely to see many peaks above 1. Then I have hydrogens that are on a carbon next to a double bond, whether it's a carbon-carbon double bond or a carbon oxygen double bond. Those usually show up around 2. So these are hydrogens on a carbon neighboring a double bond. Those show up around 2-ish. As I add electronegative atoms that's nearby, those are going to tend to de-shield my hydrogen and pull it to the left. So on a carbon next to nitrogen, it's going to end up somewhere around 3. On a carbon next to oxygen, that's going to end up 3.5 to 4. You can imagine halogens like chlorine, bromine, fluorine. Those are also going to end up in that 3 to 4 range. When I have an alkene hydrogen, usually those are going to show up in the like 5 to 6 range. Notice these are not, this hydrogen is now bonded to an sp2 hybridized carbon, right? The others are sp3 hybridized. When I have a hydrogen that's on a benzene ring, that's usually going to show up in the 7 to 8 range. An aldehyde hydrogen that's on a carbon double bonded to an oxygen, so that has the de-shielding of the oxygen plus its sp2. Usually those show up around 10. Carboxylic acid hydrogens usually show up somewhere around 12, so way down to the left. So you see this general idea is more electronegative pushes it to the left, sp2 hybridization also pushes it to the left, and then some of these numbers are just worth knowing, or keep this reference chart handy for when you're interpreting NMR spectra. The other handy thing about an NMR spectrum is it doesn't just tell you something about the chemical environment of a given hydrogen. It also tells you how many equivalent hydrogens there are. So it turns out that the area under the peaks is proportional to the number of protons that are equivalent to each other. Bigger peak, summarized here as bigger peak equals more nuclei. So what NMR machines will do is they'll have this red line. This represents area under the curve up to that point, from left to right. All right, so you see it starts as a flat line because there's no area under the curve yet. When we get to our first peak, you see it jumps up. What you can do is measure this height here. I think I'll change color. But you can measure this height difference from before it hit the peak to after, right? And you can compare it to this height difference for this peak. And then by looking at the ratio between those two, you can get an idea of the ratio of how many protons the first peak represents to how many protons the second peak represents. So if I take height 1, it wants to highlight everything there. Take height 1 and I put it next to height 2. Oh, let me see if I can manipulate this the way I want. All right, so I take it, I put it next to height 2. And it looks like I have got myself a 1-to-3 ratio, right? So this is a 1-to-3 ratio. What that means is this first peak represents, or the second peak represents 3 times as many H's. You can see in my red line, there's also a little peak over here on the right. There's a little bump for where we cross 0. Remember, this is always our TMS peak because every sample's got to have a little bit of TMS in it as our standard to set the 0 point. So over here on the left is the molecule that we're representing here. And you'll note this molecule has 3 hydrogens over here. And then it has 9 hydrogens over here. So my first peak with the height of 1 represents these 3 hydrogens. Note they're on a carbon neighboring a carbonyl carbon, which we said would show up around 2, which they did. And then my other peak, these hydrogens are farther away from any electronegative atoms. They show up closer to the baseline of 1, and the peak is 3 times as high. So that integral tells us how many protons to expect in our different groups. All right, so far you've gotten a bunch of information. I'm going to pause it there, and then I will come back to talk about spin-spin splitting, which is our last piece, which is going to tell us something about how many hydrogens are on the neighboring carbons of each peak, which sounds complicated. It is, but it gives us lots of information.